Actually, those parabolas.
Why they're shaped like they are. Yeah, a little V. Like a little V and then a little V, yeah.
Thank you. So I figured it's late afternoon and you guys are all asleep, so we're going to start with pretty pictures and then we'll worry about the hard stuff after that. So where I left off last time, what have we basically done so far? I've told you guys a little bit about the ingredients that go into a string compactification. So these analyzing supersymmetric equations of motion, SU3 structure. Last time we talked about Calabi-Yaos, which are one of the easiest and most ubiquitous types of string compactification in literature. And I told you a little bit about how to build them. So today I want to come back to some of the questions that we've already discussed in various contexts, namely, how many are there? What are their properties? And can we say anything about whether they're bounded, whether their topological properties are bounded? And what does that tell us about field theory? So to begin, let's just step up in dimension. I'm going to get to this plot in just 2 seconds, but starting in dimension, let's look at n-folds. These will be Calabi-Yau n-folds, where n is the complex dimension. So as you guys probably know, life starts simple with Calabi-Yaus. So if we say n is 1, what can we write down? Well, it turns out there is only one. As a real two-manifold, it is a T2. As a complex manifold, it is called an elliptic curve, or more generally, a genus 1 curve. The way you can show that is, remember we said the definition of being Calabi-Yau is that C1 is 0 and it's scalar. So you can show via Riemann-Roch that if C1 of Tx is 0, that implies the genus is 1, i.e. Genus 1 curve, also called, quote, elliptic curve. If we're being precise, an elliptic curve is a genus 1 curve that has an addition law on it, i.e. it has a marked point. But same thing, just one of these. So there's a lot of different ways of writing it. We've seen some already. So something like this, a cubic equation in P2, that's a torus. Another one, a weighted projective space, P1, 2, 3, 6. This guy is going to play a big role in everything you're going to do next week. You've already seen him in Vafa's lecture yesterday. This is a so-called Weierstrass description. And if I write out my weighted coordinates here, so let's call this guy z, this guy x, and this guy y, for the weights 1, 2, 3, then this guy can be written as y squared is x cubed, fx z to the 4, g z to the 6. So if I wrote this down right, everybody has weight 6 under their respective scalings. So if y goes as something that scales as a 3, then 2 y's goes like 6. Here, 3 x's, if this guy scales as a 2, goes like 6. 2 and a 4 is a 6. And 6 ones is a 6. So this is a degree 6 equation in this weighted projective space. So this guy here is what I'm drawing. This is just one description of a torus. And the coefficients here for complex one dimension, these are just complex numbers, f and g. So these guys are in C. Okay, so there's lots of different ways of writing tori, but there's just one complex Calabi-Yau one-fold. For n equals 2, same story. You can prove that, again, there's just one manifold. Lots of different ways of writing it, but one guy hiding. This is, of course, the K3 surface. And again, we can write him in lots of different ways. So, for example, P34. This guy is, thank you. My pictures just got better. Cool. Okay. Here, the topology So I should say, by the way, the things that I'm giving you are the Chern classes. Recall, the Chern classes are just related to traces of powers of the curvature. So the first Chern class is just the trace of the curvature itself. Second Chern class is related to trace of curvature squared, and so on. So here I have only one curvature invariant to write down because it's a one-dimensional space complex. Here I have two, so C1 Tx is still 0, and C2 of Tx in this case is 24. And that's the whole story for every K3. That's the only thing I can get. Okay, great. Now we are ready to talk about the fun case, n equals 3. And this is where this plot comes in. Yeah?
What about K3 orbital folds? I guess they're not CUIs because they have angular points.
So you can, are you thinking of orbifolding tori to produce K3s or taking orbifolds of K3? Okay, so you can quotient K3. Any quotient that you do of K3 has two things that are going to happen to it. Either it will have fixed points in the symmetry action, at which point you'll get a singular manifold. And indeed, this classification is only for smooth things. There are actions of K3 that have no fixed points that will lead to a smooth manifold, but their topology changing. So there's a famous one, you can quotient a K3 surface and turn it into something called an Enrique surface. And what you'll find is when you do the quotient, you'll end up with C1 not 0. So basically, anything you can try and do with symmetries either will be singular or take you outside of the class you're interested in. Other questions? Yeah? Yes, I mean, there are certain singular, yeah, good question. So you certainly can say, I would like, is the physics going to be different for singular K3s? Yeah, you can get extra light states. If you want to resolve those K3s, it's back in the family of just the one manifold. So as a smooth manifold, there is just one. Other questions? Okay, so in the early days of people, after Yao's proof of Calabi's conjecture, people are starting to write down Calabi-Yao's. They're cool, they're interesting, threefolds. There's a lot of mathematical interest in this, and mathematicians and physicists started writing down a few examples, kind of like we did on the board the other day, and they came up with a handful. And there was a brief hope, very brief, I think, in the string theory community when they first started doing this in the 1980s, that maybe there'd be like 5 or 6 Calabi-Yau threefolds, and maybe when you write down one of them, it would be like this amazing theory that is the theory of the universe, right? This one manifold. Very rapidly, that viewpoint did not bear fruit, because people started building more and more of them, and they could prove that there are many, many topologically distinct manifolds. So there are more than 500 million constructed. In fact, probably a lot more for reasons that I'll describe in a second. And this plot represents basically what we know about them so far. So what am I plotting? Here, the axes I've drawn over here. This is being characterized by the invariant Hodge numbers. Remember, this is the Kähler and complex structure that we talked about on Tuesday. This is the difference of the two Hodge numbers to tell you about Kähler and complex deformations, and the vertical axis is the sum. There are 500 million data points on this plot, and each one corresponds to a distinct pair of those numbers, so a distinct pair of Hodge numbers. I should say that this plot, as I'm showing it to you, is almost 20 years old from when it was constructed. And in the last 20 years, we've found a lot of new manifolds, but the shape has not changed. So this plot has gotten denser. It has not gotten any bigger in the last 20 years of looking. The only thing that's changed, this tip has filled in. So somebody asked earlier about Calabi-Yaus with very small Hodge numbers, like 1 or 0 down here. This guy is filled in. We now have a bunch of guys with very small Hodge numbers. Oops. Computer falling asleep. Thinking about it. Maybe. Okay, it's going to punish me for a minute. While that's thinking about it, things that I want you to notice when this thing comes back. Good. So there's a couple of features that are immediately obvious. A, we got a lot of these guys. Questions we want to ask. Again, this question has already been raised by various people in the audience in discussions. Is there a mechanism, mathematically or physically, between moving between distinct dots? So for one-folds and two-folds, there's just one manifold. There's no question about changing the theory from one to the other. In principle, if I compactified heterotic strings or type 2 strings on any of these manifolds, I would get a theory with different degrees of freedom in it. These are distinct-looking field theories. Is there a way to go from this one to this one, for example? And importantly, is there any dynamics that actually drives you somewhere in this diagram? That would be interesting if you had it. The other thing that this diagram shows you in a very big way is that it is mirror symmetric. So it reflects from left to right. So this is, of course, the very profound discovery of mirror symmetry. We'll talk more about this in just a second. But mirror symmetry says that Calabi-Yau manifolds come in pairs. Let's call them X and Y. And for any manifold that you find that has a pair of Hodge numbers H11X, H21 of Y, if this is a number, sorry, H21 of X, if you have a Calabi-Yau that has this pair, what you will find is that these numbers flip in the mirror. So the number of Kähler degrees of freedom in Y, this will equal H21Y. So Kähler in X equals complex structure in Y. Complex structure in X will equal Kähler in Y. Question? Sorry, no, stretching. Okay, sweet. Oh, great question. So you're saying, like, this is just topology, so, like, is one dot one manifold, or could it be many manifolds? There is a ton of manifolds in here. So the reason I said it's greater than 500 million, this data set, I should say, so the majority of the plots that are shown here, the majority of the points, were constructed as so-called toric hypersurfaces by gentlemen Kreutzer and Skarka. So this is their data set. These guys, what they did is they found these are distinct Hodge number pairs. There is a huge redundancy, order hundreds to thousands of manifolds with the same Hodge numbers. And even worse than that, there's some other topology besides the Hodge numbers that could even differ. So there are things that we are sure are much bigger than this. I'll try and give you an example of that in just a second. But yeah, there's lots of data points here. The number of distinct manifolds will be greater. Yeah. Absolutely, and I'm just about to talk about how we tell. So yeah, I'm going to talk about criteria to try and distinguish if they're written differently. So Yinan's point is, just because I write down a different equation doesn't mean they're a different manifold, right? We've already seen that with the one-folds. Here there are two different equations, and they're actually the same manifold. So how do you tell for three-folds whether they're the same manifold or not, even if they have the same topological data? So we're going to come back to that in 2 seconds. Okay, final thing I want you to notice, and then I'm going to get rid of these plots and we'll dive in, is there's weird shapes in this diagram, right? So the smallest point, though you can't see it here, is there are Hodge numbers 1, 1, as Federico was asking earlier. The largest data point way up there at the tip is 11,491, or its reflection. And there's this weird parabolic structure at the top. So people, after they've started writing down this data set, they were like, what's up with that weird parabolic structure? Can I say why that is there? And the answer is yes, you can, and we're going to come back to that too. So any last questions about this? And I'm going to get rid of it, and then we'll talk about stuff.
This is a really dumb question, but how do I have H11 minus H21 equals 960, and then H11 plus H21 is 500?
Sorry, say again? So you're saying...
Look at the point in the top far right.
Yep.
It looks like the x-axis, H11 minus H21, is 960, and then the y-axis...
There's a factor of 2.
There's a
Sorry.
factor of 2.
Yeah. This gets plotted different ways. I think you're right. I think this is actually twice this.
Okay.
Sorry, sometimes people plot the Euler number, and some people, the index, and sometimes people plot the difference. But you're right. Yeah, that is a good question. Other questions? Okay. Let me see if I can make these go away. Turn off. Turn off. Cool. All right. So let me just give you a couple of references really quickly from this data if you want to check it out. So the classification of a particular construction of toric Calabi-Yaus, i.e. toric hypersurfaces that I mentioned here. This is HepTH 302240. I would also recommend looking at Candelas, Nuke Phys-B, 1988, 493. So this one, the bottom paper by Candelas, this is the data set of the nearly 8,000 Calabi-Yaos built in simple products of projective space, like we talked about on Tuesday. And then the Kreutzer-Skarka set is the big one. OK, so first question I want to address is, in this plot, yeah. That's a great question. Yes, there are. There were a handful of things inspired by GLSMs, so things that were written down by like non-abelian GLSMs, determinantal varieties. Actually, my collaborators and I 2 years ago wrote down the biggest modern data set using non-toric, non-Fano ambient spaces. And I'm going to talk about that sort of new big data sets that have been produced shortly. Other quick questions? OK. So first question. Even though Matt is not here, I'm going to try and follow his algorithm for board use. Start in the middle. OK. So the first question was, so why plot these Hodge numbers, as I did? Basically, Yunan's question, is it fair to just be saying, I have a bunch of dots, like what does that actually mean? If I have different Hodge numbers for those different manifolds, the same manifold, how can you tell? So the question is, how do we tell if two Calabi-Yaos are the same? So Calabi-Yao threefolds, I should say. So what we're interested in, of course, we know that there's moduli of a given Calabi-Yao. So there's families of metrics on a Calabi-Yao that vary with complex and Kähler structure. What we're actually interested in is the topology, i.e. we want to know about deformation invariant properties and specifically construction dependent. So if I write down two different descriptions of a manifold, could they be the same? I don't want to just say the equations look different. I need to say, can I say more than that? So happily, there is a partial answer to this question. So for CY threefolds, the statement is as follows. This is a theorem by a mathematician named Wall from 1966. And what he said is the following. If I compute this data for a Calabi-Yao threefold, H11, H21, Hodge numbers that we're familiar with, the second Chern class of the manifold, if you remember this is trace curvature squared, and one more object which I'll describe. This is a triple intersection number of divisors. What does that mean? This is actually one-to-one with an integration of three Kähler forms equal to, related to, I should say, an integration of three Kähler forms J over the manifold. So remember, these guys are 1-1 forms. So you have a 1-1, 1-1, 1-1. That's a 3-3 form that will integrate to give you a number over X. And the index here, A, B, C, what is that? This is just saying I have JA in H11 of X. If I have a big Hodge number, 400 different Kähler forms, then the triple intersection numbers are take any combination of Kähler forms you like, integrate them over the manifold, and you'll get numbers every time. And you can use those numbers to characterize the manifold. So if you compute this quadruple of data, Hodge numbers, Chern class, triple intersection numbers, for two manifolds, for X and X prime, if you compute this for X and X prime, if different, so if anything in this quadruple varies, then X, X prime, not diffeomorphic. So it is certainly possible for two distinct manifolds to have the same Hodge numbers, but if you calculate the same Hodge numbers and they have a different C2, they're for sure different. What you're probably interested in is the converse of this statement. So does it run the other way? If these numbers are the same, are the manifolds the same? And the answer is converse true as real manifolds, real 6 manifolds, not as complex. So the manifolds will be diffeomorphic, the same geometry as a 6 manifold, but they might have different interpretations as a complex manifold. Now, it's a really good question, does the physics care, right? I'm putting this, did I have to introduce complex coordinates, right? In principle, I could have done this whole dimensional reduction that we talked about on Monday, and I can just use real coordinates the whole way, so where would the physics care about this? The answer is that's an open question and we're not sure. So it's very likely that if these numbers are the same, all the physics that you can actually probe with the effective theory is the same. There is one question that has been raised about Gromov-Witten invariance, so counting the number of rational curves, or the Donaldson-Thomas invariance in a heterotic theory that have to do with restricting basically worldsheet instantons in the heterotic theory to rational curves. There has been some question, Donaldson-Thomas or Donaldson-Thomas or Gromov-Witten. And although people have asked this question, could these guys differ in the case that these numbers are all the same, could these guys be the same in every way but somehow differ in some like non-perturbative physics that you care about? And no one has demonstrated that convincingly yet, that there are two manifolds that look the same but could be different actually on any level. So far all the evidence is real manifold is probably good enough for the physics, though there is a question, an open question. Okay, so what I'd really need to do would be, if I wanted to show you all the different Calabi-Yaos, I would need to have a plot that had a lot more axes than the one I just showed you. I would need to have the C2 and all the triple intersection numbers in the game too, but that I can't really plot in a practical way. Okay, so each data point in the Kreutzer-Skarka plot that I just showed you is definitely, because the Hodge numbers are different for each of those points, those are definitely different manifolds, but there could be many manifolds stacked on the same point or many distinct manifolds stacked on the same point, and you have to worry about that. Just a quick aside before I'm going to, So every bit of, this is a great question, so you can say, could there be something else, the data of subcycles, so divisors, curves, etc., those will be the same if those numbers are the same. So literally the only refined data that I'm aware of that anyone even can conjecture to be different is basically Gromov-Witten or the Donaldson-Thomas. It may prove that those actually do matter and are different for two manifolds that are the same. There have been several papers where people tried to probe this, so they wrote down two manifolds that look like they could be the same, and then tried to calculate this. One paper did a big survey and concluded that they got the same Gromov-Witten for everything. Another paper thought they might have been different, but there was some fishiness with how they calculated it.
So if we look at the D terms that are on the Abelian, doesn't that manifest in the real structure?
The D terms depend on the real structure. Not manifestly, no.
Okay.
So, or do you mean the complex structure?
The real, not a whole.
Are you thinking of the periods? I mean, you're thinking in type 2, right?
Like interval D4 theta, k of phi plus phi star. It's not manifested holomorphic.
That's right.
So.
Yep. So there's a whole special geometry thing in play, for the prepotential, for example, all this.
1 equals 2, just equals 1.
Mm-hmm.
So
You're talking about the Kähler potential for n equals 1.
yeah.
Sure. Again, it's not manifestly. So the hard part with the Kähler potential is actually calculating that for anything non-trivial, which we don't have a good description for.
Why would I expect it to?
I wouldn't. On the converse, I would actually expect it to be the same. I mean, my perturbative instinct is, as we were doing this dimensional reduction, no one forces you to use complex coordinates in any of this. So you should just be able to formulate the entire theory in terms of a real manifold. For the perturbative theory, that's very clear. The non-perturbative effects, I think there's more of a question about whether something could talk to each other in a weird way, talk to the complex structure, the fluctuations. Question?
Yeah, so how the triple intersection gives you sort of the data?
In n equals 2.
Right. How would that
So there's different, Donaldson-Thomas can appear in different contexts in different ways. Where I actually had in mind with this was in heterotic, for example. Worldsheet instantons are not just a Gromov-Witten counting of rational curves. They will be a counting of sheaves restricted to rational curves. So in n=1 theories, Donaldson-Thomas can be a little different than just what you're describing. There's sort of an analog of Donaldson-Thomas, but I agree the language is a little ambiguous. Yeah?
Why these particular Hodge numbers?
These are the only independent Hodge numbers for a threefold. So for a threefold, this is all there is. And actually, where I was about to go was just briefly to tell you what the story is for fourfolds, and then I'm going to come back to threefolds. So for n=4, what can we say? There is no analog of Wall's data for fourfolds that has been proven, though I think there is a belief that something similar should apply. What, in principle, do you have? So here, C1 is 0, as usual. We have here C2, C3, and C4 for the Chern classes. And we now have Hodge numbers. And related to the question that we just got asked, the only two non-vanishing Hodge numbers for threefolds, that was those H11 and H21. For fourfolds, we have H11, H13, H12, and H22. These guys satisfy one linear relation. So one linear relationship. So in fact, only 3 out of the 4 are independent. And the 3 that people normally write are H11, which is again Kähler moduli, H13, which is complex structure, and H22, which does not have quite as good a geometric interpretation just in terms of wiggles on the manifold. What this guy is physically, it has to do with the variation of form fields that you can write down on the manifold. So specifically in the language of M theory, this is related to fluctuations in G-flux. So variations in G4. So this plays a big role in F theory. You're going to hear more about this in 4-dimensional compactifications, I believe, from Professor Weigen next week. So what you would need to do for fourfolds would be to analyze this data. In principle, you would have other intersection numbers you could compare, and you can ask, again, are fourfolds the same? I should say that the data set of fourfolds is ordering on the order of magnitude hundreds of thousands, though it's going to be huge. So you could repeat the calculation that Kreutzer and Skarka did for fourfolds, but this is in all likelihood currently beyond the reach of modern computers. So there's the sheer computational time it takes to generate these data sets is a big pain in the butt. So the current data sets are smaller, but we believe the number of fourfolds is very large indeed. Okay, good. So now I want to come back to observations that we can make about what we know from this data so far, specifically the plot that I just showed you. So observations / questions. What do we want to observe? As I mentioned, data set continues to grow, but only getting denser. And if I have time today, I will finish. I'll give you an example of that. I'm going to show you the newest big data set of Calabi-Yaos that was due to my collaborators and I, which is this guy, 1507-03-235. I'll do that at the end if I have time. Things that we would like to understand for physics are geometric substructure. So as I mentioned before, we need to know a lot of things about Calabi-Yaos in order to pull out the physics. As Professor Waffe very nicely showed us yesterday, fibrations play a huge role in string dualities. If you have those in play, that's going to tell you a lot about the different kinds of theories that you can get and how they're related to other corners of the string landscape. We care about what I'll refer to as blow-ups and contractible cycles. I'll define this properly in a second, but morally, these are avenues that you can do to change the topology of the Calabi-Yau. These are things you can shrink or twist within the geometry to turn it into another Calabi-Yau. This will tell you about how things are connected. And these, of course, also play a role in physics. For those of you that do type 2b, large volume scenario, etc., This is, again, the Swiss cheese structure of the manifold, which is very important for non-perturbative effects and other things you'd like to write down. And the question, which is related to this one, can we move dynamically? So in a given theory, if I start with one Calabi-Yau background, can I move to another? Can I move to something non-Calabi-Yau within the effective theory? There's two ways to do this, and I'm going to review one of them for you that we know of. Both of these fall under the name of geometric transitions. And these are geometric transitions. And morally, flops happen in the Kähler moduli, conifolds happen in the complex structure. Now, as we've also mentioned, there is something called Reed's fantasy. Sounds like a symphony, doesn't it? Like if you this is Miles Reed, the mathematician. His fantasy is that all CY manifolds, and in fact, here he's even a bit more broad. Here he actually believes all SU3 structure manifolds, not just Calabi-Yaus, should be connected via mechanisms above. It is a fantasy because this is not yet proven. However, for basically all the constructions that we know about, including the ones that give us these data points that I showed you, in practice, it is possible to find explicitly chains of these transitions that take you basically everywhere. So this is true for everything we know about, but we have no proof that it's true more generally for Calabi-Yaus. Okay, so let's now look in a little bit more detail at one of these. Probably this is familiar to many people, but it's important enough I want to review it here just briefly. How do you see two manifolds that get connected by one of these mechanisms? How does that actually happen? So the idea is that we move to singular points in moduli space of the Calabi-Yau. We fix them in some way, and we get new Calabi-Yau. This was an example of the surgery that I mentioned as one of the methods of constructing new Calabi-Yaus. That is the idea. Oh, I'm in the right place already. So let's consider a classic example of two manifolds that can be compared this way. The first one is the simplest guy we can write down, the quintic. And the second, I'm going to write in this way. The Hodge numbers of these guys are, frequently these get written as superscripts, 1, 101, 1 Kähler modulus, which is an overall volume, 101 complex structure moduli. And here, this guy has Hodge numbers 286. 2 Kähler moduli. The notation, again, just remind you, the ambient space is P1 times P4. That's a 5 complex dimensional ambient space. Each of the columns tells me about the degree of an equation, right? So this is a multi-degree 1-1 equation. This is a 1-4 equation. 2 equations, 5 dimensions, gives you 3-dimensional solution. So that's a Calabi-Yau threefold. Let me call the coordinates of this guy x and the coordinates of this guy y in these ambient spaces. And I can label my polynomials as p and q, which you guys may not be able to see so well. Polynomial p would be of the form x0, linear in y, x1, linear 2 in y. There are 5 coordinates for p4, so these are any linear in the 5 coordinates I choose to write down. x0 and x1, I can use the scales and the fact that this equation equals 0 to just get rid of these overall coefficients or soak them into the L's. That's one equation. And the second equation is going to look like a linear in the x's and quadratics in the y's of this form. So at the moment, these are two totally general polynomials of the appropriate bidegree. And of course, on the quintic side, I have just one polynomial that will look like a0 x0 to the 5th, a1 x0 to the 4th x1, blah, blah, blah. equals 0. Okay, so I have two different Calabi-Yaos. Sweet. I wrote down defining equations for the two of them. Now what do I do with this? Well, the observation that you can make is that because this guy depends only linearly on one of its ambient coordinates, I could write this set of two equations as a matrix equation, right? So I could write this as linear 1, linear 2, q1, q2, acting on x0, x1 is equal to 0. Now, I know from the definition of projective space, the fact that these coordinates scale, that x0 and x1 are not allowed to go to 0 together, right? They can't vanish simultaneously. So in order for this equation to be consistent as a matrix equation, I better have, let's call this guy m, I better have the determinant of m is 0. And this is because x0 equals x1 equals 0, not allowed. Okay, so far so good. So the determinant of that equals 0. What is that? That is in the y-coordinates. So I don't want to hide things too badly here. This is in the y-coordinates, linear 1, q2 minus linear 2, q1 is 0, right? And now if you look at what I've just defined, probably most people have seen something like this before, but just to do it quickly. If you look at what I've just defined, these y's were the coordinates of P4. So I am saying that this manifold exists if and only if this auxiliary equation, which is a degree 5 polynomial in P4, is 0. So I am telling you that this manifold can be written down only if a quintic can be written down, a quintic in the coordinates of P4. Now, in principle, all coordinates in the quintic of P4 describe this manifold. So the question is, are these guys the same? This is a quintic in P4. Even though I wrote it differently, this looks like it's a quintic in P4. It is, defined equivalently by this determinant of the matrix being 0. So are they the same or not? The answer is that they are not. So even though this guy implies a quintic, the observation is that this guy, L1 Q2 minus L2 Q1, is singular. So it is a quintic, but it's a spiky quintic. So if I were to draw this as curves, instead of having a smooth curve, this would be on the quintic side. Here, in the singular geometry, I've got something with non-manifold looking points, spikes in it. I can say, where does it go singular? That's actually easy to write down too. This guy goes singular at the points L1 equals Q2 equals L2 equals Q1 equals 0. Those are your singular points. Now you say, why are those points? How can it be singular over something bigger? Notice this is a 4 complex dimensional space, and I have 4 equations being 0. This will be singular when all 4 are satisfied. So those are points inside P4. And in fact, there are 16 such points you can work out. 16 points in P4 where this manifold goes singular. So it's a perfectly good-looking quintic, except at 16 points, goes spiky, and thus I claim it is not the same as the generic quintic that we wrote down. So what do you do with that once you get it spiky? Well, you can fix the spikes. So what you do is as follows. You take your spikes in the manifold, here's the singular points, and you perform what in mathematics is called a resolution. You're going to replace those points with 2 spheres. So this is S2, which as a complex manifold is equal to Q1. So there's 16 points you're going to cut out of the manifold, and you're going to replace them with a sphere. The name conifold has to do with the fact that the thing that you're shrinking to make the manifold singular, if you were approaching this from the quintic side, so if you wanted to take a generic quintic and make it look like this, you have to tune some 3 spheres to 0. If, on the other side, you wanted to come back to the singularity, you would tune 2 spheres to 0 inside the manifold. So by tuning 2 different manifolds, you can hit the same singular point. So what the claim is that these 2 manifolds I wrote down, P4, 5, this is referred to as the deformation side of this geometry, because if I started with this singular geometry and I just change the defining equation to make it a generic quintic, I'll smooth it back out, I'll lose the singularities. Here's x singular in the middle. This is my guy defined by the singular quintic, L1 Q2 minus L2 Q1. And on the other side, I have the resolved conifold, which is P1, P4, 1, 1, 1, 4. So this is resolved. So again, notation, people say the conifold is the spikes, so named because in algebraic geometry, actually mathematicians are a little annoyed at us for calling it conifolds. This is physicists speak. In mathematics, this is just a node. That's all it is. But it looks a little bit like a conical singularity because it's spiky, so hence the name conifold that physicists gave it. So you can start in the middle at the conifold, and you can go left into the deformation, you can go right into the resolution. And if you start at a singular point, you are connected to 2 different manifolds. As smooth manifolds, they're topologically distinct, but they share a singular point in their moduli space. Yeah?
Why does this always have to do with S3s and S2s?
So this is because, so to do this properly, so the S2s you can probably see, right? Because this is just how I resolve these particular point-like singularities. So those guys I can collapse. I should say, by the way, that this P1 is this guy. So it's actually very manifest in the defining equations that I'm writing down. To see the other side, what you're doing is tuning the complex structure and the quintic to hit this point. If you write this down in terms of periods, these are tuning 3 cycles. And you can show the ones you're tuning are topologically as 3s.
You can have more in general.
Absolutely. Yeah, I mean, S3 is just a loose statement. But in general, yes, it will just be some 3 cycles that you're tuning to 0.
And you can blow up there. You don't need to blow up.
For this particular type of singularity, this is the resolution that is crepant, so it will preserve the topology. For other types of singularities, you can have other types of resolutions that come in. Other questions? OK, sweet. By the way, by topology here, I should have been a bit more specific. Preserve C1 is what I meant, so keep it Calabi-Yau. OK, cool. So this is an example when Reid talks about his fantasy of all Calabi-Yaus being connected. This is an example of how you could do that. So for these manifolds that are written by these sort of matrix equations with degrees in them, everything that can be written of this type. So we classified 5 on Tuesday. You can build 7,890 of them, and you can prove that every one of them, by this type of tune it singular, blow it up, blow it down, tune it singular, every one of them can be connected by this process. Now, the cool question is, what does this mean dynamically, and can you track it? And this was answered affirmatively by Strominger. So dynamically, can you track the physics through a conifold transition? And in type 2a, Strominger showed that indeed you can. And to do this, you need to move beyond the perturbative string theory. You need to add in branes. So if you imagine that you have, in type 2a, D2s wrapping the P1s that shrink to 0 size, at the middle point, you're going to get extra light states, and you can have a Higgs and Coulomb branch of the theory that is associated to this singular geometry that gives you the deformation and resolution side. So in field theory with a non-perturbative completion, in type 2a, this is well understood. Yes, you can do this dynamically in field theory. Dynamic transition. I should say that the n equals 2 structure of type 2a, and you can make arguments about type 2b, understanding type 2a, you can use the mirror, etc. The fact that you were able to do this used the n equals 2 structure in a huge way. So having the hypermultiplet structure in an n equals 2 theory was very crucial to Strominger's argument. For n equals 1 theories in 4 dimensions, i.e. heterotic, etc., it is unknown if you can do this dynamically. We expect that you can, but no one's written it down. We don't know how to complete the theory. Other questions here that matter. If I wrote this down. Oh, I should say, just because you can follow the dynamics doesn't mean that there's any kind of flow. So some people, Philip Candelas included, he wrote, he looks at this plot of all the Hodge numbers that we just saw, and he thought it would be really cool if there's some sort of broader dynamics in string theory that force you to kind of trickle down that plot to someplace special. So people have thought about that. They've said, if, in type 2 theories, if I could follow the effective theory across one of these transitions, is there anything that forces me to flow towards a particular Calabi-Yau? That would be cool if it is. No such mechanism is well understood, but I should say there's a very famous paper by Silverstein et al., which I did not write down the archive number for, I'm sorry, but has the catchy title, Beauty is Attractive. And their basic idea was that points of enhanced symmetry may create a potential in the effective theory that could draw you to the transition point. So this does not give you dynamics across the whole web, but it could say that if you have a transition point like this available in the theory, perhaps there could be a potential flow that could force you to change topology and turn a corner like this. This is just one example, and there's a ton of open questions about this, but I think it's fair to say no one properly understands the dynamics of topology changing fully. Any questions about that? Yeah. I mean, in practice, it's a flat direction for the things that we understand. I mean, so there's just no dynamics at all. So, I mean, these guys, they came up with some arguments to sort of argue there might be, in the presence of certain non-perturbative effects, you might actually be drawn to these enhanced points. Whether you believe those generically or not, read the paper and decide. But other questions? Yeah. Matter? I mean, on the contrary, actually, what this is saying, I mean, if you believe their argument, you're actually saying that you get drawn to the point with the most light states. So it's the other way around. So these singular points, actually extra light states that are generically massive, come down and become light. So what they're saying is the more light states, the better. You get drawn to those points of the biggest it could possibly be. Okay. Good questions. So with that, I now want to switch gears and get into this question of boundedness and whether we can say something about all Calabi-Yaus. So not just the data sets we've built so far, but what do we understand more generally? And to do that, the way I'm going to tackle that is I want to look at fibrations. Within CY3s. So, as a beginning aside, the existence of a fibration and remember, this means you can stack something over something else. That's what fibrations mean. And mathematically, that means we can write a projection from X onto another space B. This is deformation invariant. Deformation invariant, i.e. topological, for all CY n-folds with n greater than equal to 3. This was proved by mathematician Wilson in the early 90s, and I would recommend looking at 1206-5721 for a review of some results on this. Why n greater than 3? For K3, there's just one K3, remember? And as you vary the moduli of the K3, you can move the existence of a fibration in or out. So I mentioned that you can write a K3 as a T2 fibered over a P1. You can vary the moduli to get rid of that fibration entirely. But after you move past n equals 2, that no longer is true. So for every 3-fold, 4-fold, 5-fold, if you have a fibration, every deformation of the geometry will preserve that fibration. So this is not something that you can get rid of. It is a fundamental characteristic of the geometry. Okay, Now here's the cool part. I'm going to do this on another board because it's important. A crucial result and this is due to mathematician Mark Gross in '94, building on work by Antonella Grassi from '91, is the following. The number of T2 fibered CY threefolds is finite. And moreover, they have finite Hodge numbers. I should mention as well, you might say, okay, well, I just said fibration. How many different things could be stacked over other things inside Calabi-Yau's? You can actually prove that there is essentially only 3 types of fibration that can arise in a Calabi-Yau. You can have a Calabi-Yau threefold, which is a T2 fibered over a 2-dimensional base manifold B2. That's the case that this finiteness result applies to. You could have a K3 fibration fibered over a P1. That's another option. And then there is a final option, which I'm not going to really be concerned about, which is a special quotient of this guy, which is something called an Abelian surface, which is just a particular quotient of a K3 over P1. This is an aside. This is basically a subset of case 2. Yep?
So maybe misremember, I thought the proof of mirror symmetry relies on the fact that all Calabi-Yau's T3 fibered over something.
So good. So there's different notions of fibration in play here. So you're thinking about SYZ mirror symmetry, which is based on T3s. There are ways of thinking about T3 fibrations as real manifolds. The statement here is about fibrations as complex manifolds. So there are conjectures, I don't think they're actually proven, about T3 fibrations as real, and certainly SYZ is based on that and is hoped to generalize to all. The statement here is about a holomorphic projection map which preserves complex structure in which all the pieces are complex. Good. Okay, so there's basically these two. This one and this one, so the finiteness result applies here. This is the hard case. Once you have this one, you can actually talk about finiteness of this one too. So morally, this is about the finiteness of all fibrations. I'm going to focus on T2 fibered guys for a second. All right, so this guy is finite. The proof is not constructive. So this is related to, as I mentioned earlier, the so-called minimal model program in mathematics, which is basically how mathematicians are trying to classify complex geometries of various types. This is related to Kodaira's classification of complex surfaces and is being used for now higher dimensional algebraic varieties by people like McKernan and I'm spacing the name of the big dude at Utah. They'll come to me. Nope. Okay, in a minute. Anyway, some very famous guys who got like Fields medals and stuff have been working on this. What they have been trying to do, the basic idea, is they consider what's called birational equivalence. The equivalence. And this is very similar to the idea of conifolds that we described here. What they do is they look in a given geometry for things like this P1. So they hunt in geometries for when you can have guys, things like this, that can be contracted, i.e. volumes that can collapse, to give you a singular thing that you can then fix again. So they consider basically all ways of trying to blow up and blow down, to contract various cycles in order to connect various geometries. So what they basically prove is that there's a finite number of bases, B2, for these Calabi-Yau's, and they give a finite number of ways that you can mess with those bases, i.e. blowing up and down in the base, that could generate consistent Calabi-Yau threefolds. Okay, so far so good. So their proof is not constructive. So they prove it's finite, but they do not enumerate all of them. They can prove that the Hodge numbers are finite for these elliptically fibered guys, but they don't tell you the number. So actually, a lot of the work that Waddy Taylor at MIT has been doing is trying to actually sort of practically follow this program and generate all of them. I'll talk more about where we're at with that in just a second. Haken, thank you. Christopher Haken. Miriam saved the day. Christopher Haken is a very nice guy. He actually just visited Virginia Tech last fall, so please don't tell him I forgot his name. Okay. Very clever guy. Excellent, big cheese in the minimal model program. All right. Cool. So I should mention, I mentioned this earlier in the discussion session, similar results, almost there, for fourfolds due to mathematicians Dicerbo and Svaldi in 2016. There's some technical fine print that means that this proof is not quite complete compared to the threefold case. If you're interested in the details, ask me after. But I would say 95% there towards proving finiteness of all fourfolds, elliptically fibered fourfolds. All right, so here's the questions we now want to ask. Question? Yep.
Did you say that this result holds for all vibrations, not just for
It holds for, you can generalize, the results they used here, you can generalize into K3. And this is all for Calabi-Yau 3, that you have as holomorphic vibration. Again, the question of could you have real vibration substructures? This is all about holomorphic structure. No. It is an extremely formal proof. So they don't have an order of magnitude estimate. They give a set of 5 minimal bases from which everything else can be birationally equivalent. So they give a set of building blocks, and then they don't explain how high the birational chains go. We have better ideas about this now through physics, but mathematically that was all they had. OK. So I should point out that this proof of finiteness due to Mark Gross was actually motivated by trying to prove that all Calabi-Yaus are finite, threefolds. So he was hoping that he could observe structure that might help him prove something a bit more generally. And that didn't quite happen, but there are hints about where you go from here. All right. So, the question, does this extend in any way to all CY3s? In order to answer that question, the first one we have to ask is, from what we understand already, what fraction of all the Calabi-Yau 3s we know about, namely all the guys that I showed you in that big plot to start with, what fraction of those emit vibrations? So we'd like to know this in general, but first, what fraction of CY3s emit vibrations? And next question, can a fibered CY be connected in the same sense that we just did for conifold transitions there to non-fibered? And could we try and classify how many different ways you could lose the vibration, for example? OK. So to begin to answer this, let's start with the data set that we know already. So of the 500 million, how many fibered? Question mark. And the answer is this has been done explicitly for various data sets. So let's start with the complete intersection Calabi-Yaus in products of projective spaces, this simple historic class of 7,890 manifolds. This is greater than 99.5% of those manifolds emit vibrations, elliptic vibrations specifically. There is an estimate for the toric hypersurfaces, which is a little cruder, and various people are working on improving this, which is greater than 90%, should emit vibrations. And for the data set of CY fourfolds that have been built so far, greater than 99.9% of all fourfolds emit elliptic vibrations. Now, you could ask, okay, some don't, so what is that actually telling me? The observation is that the existence of a fibration seems to be correlated to the size of the H11 moduli space. So as H11 gets bigger, everything appears to have a fibration. The only exceptions, and the reason that this structure was not observed earlier, the only exceptions are extremely simple manifolds like the quintic. So the quintic has H11 of 1. This guy does not admit a fibration. It's easy to prove. This is easy to see because there's just one volume, so you can't really have one thing stacked on another thing with independent volumes, right? So people built easy Calabi-Yau's first, and they didn't notice this. As you start cranking up H11 for either 3-folds or 4-folds, literally everything is. So mathematicians have made conjectures, and physicists, including myself, are working on trying to prove this, that as you increase H11 beyond a certain bound, so conjecture, if H11 of x3 or x4 for 3-fold or 4-fold is greater than m, then fibered. And specifically here, I'm interested in T2 fibered. Now you might say, what is m? In the data sets that we have, we believe that this is about order 10. So if you have something that has order 10 or more, this number is actually smaller. I know this off the top of my head. For this data set, the CC3 folds, in fact, you can prove everything in that data set for H11 bigger than 4 admits vibrations. So H11 of 4 is pretty small. For others, I think the largest examples that anyone has conjectured, and there's some mathematical evidence that after it gets to be about order 10, you would expect everything is going to admit a fibration. So this is cool because if this is true, first step to proving finiteness, if you can prove that everything is fibered as you increase H11, that tells you that as you increase H11, you will have fibrations, and hence you will have finite Hodge numbers. So that would actually give you a proof of the finiteness of the Hodge numbers, and you can get H21 by mirror symmetry, right, for all Calabi-Yaus. That doesn't prove that there's a finite number of Calabi-Yaus. To do that, you would have to answer, wherever I put that question, you'd have to ask, how can a fibered and a non-fibered Calabi-Yau be related, and could you prove a finite number of connections of that type? So in all seriousness, we're getting a lot of new tools to be able to address the finiteness issue, and I'm actually quite hopeful that this could be pushed forward in a meaningful way. Groups that are working on this seriously, mathematicians, including a bunch of people in the minimal model program, are thinking about this. I should also say, so I have some recent papers on this. Waddy Taylor at MIT has done a lot of constructive work of building, and I should say his students, some of whom are here, have done constructive work of basically explicitly building the formal proofs that these guys did here. They actually built them, the manifolds, explicitly in many cases. Okay, so the guess is here, where did I put it? We think that m is approximately 10. All right, now here's the cool part. Several cool parts. The first things that I need to observe about this, so first, the shape of the Calabi-Yau. So I said everything above a certain Hodge number that we know about so far is fibered. And I told you about the shape of those parabolas in the Kreutzer-Skarka diagram. A neat thing is that everything on that upper boundary, in fact, the complete boundary of the Kreutzer-Skarka plot, is an elliptically fibered manifold, and it is a provably extremal elliptically fibered manifold in the sense of 6-dimensional compactifications of F-theory. So shape of KS Hodge plot, it is known that the boundary are all T2 fibered, or elliptically fibered. The shape, this parabola, can be described as conifolds between elliptically fibered manifolds. Conifolds of T2 fibers. And in fact, if you look at all the different ways that you can shrink cycles for elliptically fibered things, they actually sweep out exactly those parabolas that I pointed out to you. And moreover, the ones that we know about already, so things like, e.g., the manifold with Hodge numbers H11, H21 equals 11, 491, this has been proved to be extremal via physics, not mathematics. So this is the largest Hodge number that can belong to any T2 fibered manifold. This has been proven by Taylor in 12050952 using anomaly cancellation considerations in 6-dimensional compactifications of F-theory. So he said, if you hand me an elliptically fibered manifold that has larger Hodge numbers than this, it cannot be a consistent F-theory vacuum in 6 dimensions. So if you believe that any T2 fibered manifold should be a good background for F-theory tells you that nothing exists with bigger Hodge numbers than this. Various people are trying to prove that mathematically through different means, and that's still an open question. But physics strongly suggests that this is the bound for any elliptically fibered manifold, and we've already hit it. Yeah? Yes. So the special numerology is, you can argue, basically, what's a simple way of saying this? So if you think about the H11, these are divisors inside the threefold. You have a fiber-based structure. So you have a T2 over a B2. You can prove that the maximal base that you can write down is the surface F12 blown up at 24 points. This corresponds in the heterotic F-theory duality that Vafa was mentioning yesterday. This is the tensor branch of 24-point-like instantons in the 6-dimensional heterotic string. And then you can ask, if I have F12 blown up at 24 points, and if I singularize this fiber as much as possible and then fix it again, blow it up, the maximal numerology I get is the 491. So that's a long answer. It's not terribly intuitive, but there is a good physics reason for why that's the case. So it's sort of the extreme limit of these 60 theories, which heterotic and F-theory are giving you the same answer. OK. And I'm almost out of time for today, so I'm going to finish with one more important point, and this is very related to another thing that Professor Vafa was saying yesterday, which has to do with structure in the string landscape. Some things that my collaborators and I noticed a couple years ago is, as we started looking at whether things were fibered or not in these general data sets, one of the first things we observed is not only, as you crank up the Hodge numbers, does everything admit a vibration, everything admits more than one vibration, which is weird. So observation, get rid of all of this. Not only are generic Calabi-Yau threefolds that we know about, and we believe this holds more generally, but haven't proven it yet, not only are these guys T2 fibered, they are all multiply fibered in the following sense. Instead of having just one map, pi, which takes you from X to, in this case, a base, two-dimensional base with a T2 fiber, what you have is an X that has many projections with different projections pi 1, pi 2, up to pi n. So you have a diagram that looks like this. You have many different maps originating from the same manifold that take you to topologically distinct bases. Now, this is interesting for the following reason. Professor Vafa told you that when you have vibrations, you have string dualities. So for every vibration that you can find, a K3 vibration, a T2 vibration, you can use this in either 6 dimensions or 4 dimensions to write down dualities between theories. For example, remember he said in 6 dimensions you have heterotic F theory. In 4 dimensions, you can do, again, het F in 4D. You can do heterotic type 2A. There's lots of interesting dualities you can do. And anytime you have a vibration, you have a duality. It's pretty fair to say. So if you have a lot of fibrations, that means you have a lot of dualities, all of which are centered on one manifold. What that means is within the data point of your different compactifications, if this is Vafa's landscape, here's his chosen points in the swampland. What this is saying is that if you just have a compactification arising from a Calabi-Yau, these points all appear to be linked with a huge degree more redundancy than we'd ever realized. So instead of getting, if I give you 500 million Calabi-Yaus, instead of getting 500 million different theories, the fact that these guys are all different, different theories from type 2A, type 2B, M theory, F theory, etc., heterotic, what you're saying is that there's a huge redundancy. So any manifold is giving you many different fibrations. This is somehow grouping together huge families of theories that are going to give you the same effective physics. Okay, so that's interesting and we want to know about it. Let me give you an example of how you see that, just briefly. And then I will carry on tomorrow with some other features. So how do you see that something is fibered in two different ways? And what does that mean for you in terms of, again, dualities or the types of physics that you can work out? So let me give you an example of a fairly complicated threefold that has some structure, but I can point out some simple features. So let's look at this guy. You're like, man, this is almost 5 and she's writing all those numbers. Why is she doing this to me? I'm sorry. Will kind of be worth it, maybe. All right, there's a threefold. Why is it a threefold? I've got a 1 plus 2 is 3, 4, 5, 6 dimensional ambient space, 3 equations. That's a threefold. Now I want to show you the following structure. Look at just this block up here. So this is 2 equations of degree 1, 1, 1, 2, if I look just at those numbers, in an ambient space P1, P2. That's a 3-dimensional ambient space, 2 equations. This part of the degrees that I'm giving you is describing a T2. Now, I can't just ignore all the other degrees, but if I were to fix the coordinates of these bottom 3 P1s, then I would be left with an equation which is just of these degrees in this ambient space. So what this is saying is if I fix the coordinates here, I will be left with the equation of a torus. That is a fibration. So just from the structure of this configuration matrix, I can read off that this guy admits a fibration over a base, where the base here is a triple 1, 1, 1 surface in P1, P1, P1. This is, in fact, the Del Pezzo 3 surface. So just from looking at the degree structure of this manifold, again, pick a point here, solve this first equation, plug it into the second, you'll be left with the equation of a torus. That's why it's a fibration. So this is saying that this guy, X, is fibered over dP3 with a T2 fiber. Okay, so far so good. I just read that off of the degrees, and I was able to say that this thing admitted a fibration. But there is no order to the way that I wrote this ambient space, and it doesn't matter in which order I write the columns either, because these are just giving me the degrees of the equation. So I can permute rows and columns, and let me do that really quickly, and then you will be free. So I can rewrite the same manifold in the following way. P2, P1, P1, 1, 0, 1, 0, 1, 1, 1, 0, 2, 0, 1, 1, 0, 1, 1. So if you look at this compared to what I wrote the first time, it's just permuting stuff that doesn't matter. Order the ambient spaces, order the equations. They're the same equations in the same ambient space. And here, if I draw the line up here, if I look at what I've got a 4-dimensional ambient space. If I look at the degrees, each degree across each row sums up to 1 more than the degree of the ambient space. This is 3 equations in a 4-dimensional space. This is again a T2. And the points that I would have to plug in order to get the equation of a torus are points in P1 times P1. So here, this guy is the same manifold X, which is now fibered over base, P1 times P1. These are topologically distinct bases, but it's T2 fibered manifestly in two different ways. Now, I spotted these just using a super cheap trick, which is just look at the degrees and spot two tori floating around in the degrees. This is what we refer to as so-called obvious fibrations. There actually are tools to systematically find all fibrations. And you can say, how many do you get? So if you search for obvious fibrations, the answer is that you get for three-folds order 10 fibrations per manifold, and for four-folds order hundreds. If you search for ones that aren't obvious, so that can be hidden from you if you have an exhaustive search, that number gets up to, in extreme cases, thousands for a threefold. So you have thousands of different fibrations within one threefold, all of which are giving you a different handle on the degrees of freedom in that theory, which string backgrounds you can use it on, and which other string theories it's actually related to. So I'm going to stop there because we're all tired. We'll play with the consequences of this one last time tomorrow. Yeah.
Are there any examples of different symbols showing the same underlying structure?
What do you mean by underlying smooth structure?
I mean, they are the same real manifold, but are compact structures that make the same manifold into different compounds.
Okay, so that's related to this Wall's theorem conjecture. There are no known examples of anything that is the same as a real manifold that is different as a complex. Could exist, it is not ruled out by Wall's theorem, and people have been interested to try and find a difference. So far, there is no difference that could do any impact on the physics that has been demonstrated in the literature to date. So far, when the Wall's data is the same, we have all the evidence so far indicates the physics is the same. That's not a robust statement. If you find a difference, write a paper and it'll be a cool point if you can find something that's different. But to date, we have not seen anything different. That's great. So why did I say there's more than 500 million? So Yunan's point is there's 500 million toric polyhedra that I can use to build hypersurfaces that gave me that plot, but I haven't computed the Wall's data. However, for the low Hodge numbers, people have computed triangulations of the Kähler cone, and they've shown how many distinct. It is just enormous. So the actual belief is that there are actually, this is going to be quite a bit more than 500 million once you actually distinguish all this data. So we don't have the answer, we don't have the number for the full data set, but for H11 up to about order 10, these triple intersection numbers have been computed in some cases, and the number of distinct options when you do complete triangulations is enormous. So it's going to be big, but we don't know how big. That's right. So they don't change the Hodge numbers, but they can change the triple intersection numbers. Yes. So you can have, so you're saying like purely H22 transitions, or? That's a good question. So certainly people have considered the analog of both of those. So Kähler and complex structure, conofold or flop type transitions for fourfolds. You can have weirder stuff happen, which probably does involve H22. So basically this is about the dimensionality of the various subcycles you're shrinking. And because you have a bigger manifold, you have more possibilities to shrink cycles in fourfolds. So that's a good question. I don't know off the top of my head, and people have looked at how four-flux, the 2-2 forms change under this process, and I know they can, even under regular conofolds. So basically, we expect that fourfolds will be richer. There'll be more transitions, but I don't know quite precisely how different they are off the top of my head. Dave Morrison has looked at this. If you look for Morrison and Hans Jokers, they have some papers playing with at least some of those transitions. Yep. So if you start with, for example, this guy that I mentioned, this elliptic fibration over F12 blown up at 24 points, if you do conofolds from him, you can sweep out that entire upper boundary. So there's just a cool chain. This was actually started to be worked out actually back in Morris and Vafa original papers on F-theory, And then Waddy and collaborators did this much more explicitly, and you can just, you can watch the transition all the way across, and you can get quite a ways down these diagrams as well through conifolds explicitly, all within elliptic fibrations and F theory.